I think we can move on to the next session. This now, we will shift a bit the focus more into the environmental assessment part in SSbD. So I would kindly ask Mattia Costamagna to come on stage to give us a presentation on the introduction of LCA.
Yes.
Thank you.
Hello. Can I? Okay, good morning to everyone. It's a pleasure to be here. Today I will introduce the concept, the methodology of life cycle assessment. First of all, my name is Mattia Costamagna. I work for Project Hub 360. We are a consultancy company located in Turin that deals mainly with the topic of innovation and sustainability. And we are partner of the project Integrano. Since I have to speed up a bit, I have prepared a lot of slides. This slide will be shared with you, so please try to stay with me. I will try to jump from one slide to another to help you understand something more about life cycle assessment. First of all, I will start, okay, here is what do we see? I will start to set the context. The context we are moving in is the one of sustainable development, sustainability. Here you can find the definition provided by the Brundtland Conference. They said that sustainability is the development that meets the need of the present without compromising the ability of the future generation to meet their own needs. So here we see a gap, not a gap, but a shift from the title, because the title was related only to environment. Here we are talking about everything, more or less. And that's the main concept. Sustainability is not only related to the environment, but also to people and to prosperity. It's also to the social dimension and economic dimension. And this requires to address sustainability according to an holistic approach to take into account all these dimensions. According to the United Nations, they develop the Sustainable Development Goals that are targeted to guide the world, all the nations toward a more sustainable future. They are divided in 17 targets. And the question that we ask to ourselves is, can we measure sustainability? How can we measure it? In general, when we want to measure something, we need, first of all, to define what we want to measure. Then we need a unit of measurement, a tool for measuring, and a procedure, a methodology. In the case of sustainability, the methodology is the life cycle thinking. In the presentation before, you showed this term you saw this term on the slides. And the concept of life cycle thinking is to use an holistic perspective to address the three dimensions of sustainability that we saw before, environmental, social, and economic, by analyzing the environmental impact, the possible effect on the cost, the risk for society, with a life cycle perspective, so taking into consideration on the life cycle of a product, a process, or a system. Here you can see some references, some guidelines to follow, to perform the analysis. And now let's move to the environmental dimension only. This is analysis through the life cycle assessment. Here is the definition. Basically, LCA allows to evaluate the environmental impacts of a product, process, or service through every single stage of their life cycle. Here you can see two standards, two ISO standards that set the framework to perform an LCA, and here is a book with all the information. It's called the Bible of LCA from someone, if you are more interested in this topic. Basically, when you arrive to perform this kind of analysis, you have to keep in mind that you have to follow 4 different steps. The first is called goal and scope definition. Then we have the inventory analysis. They have the life cycle impact assessment and the interpretation of the result. All these steps are interconnected and can be repeated several times. Let's start from the first one. In this case, you have only to think, to clearly set in your mind what you want to analyze, why the reason why you want to analyze this, and you have to keep in your mind because at the end, when you ended up with your result, you probably have to write a report, a document, and all this information have to be clearly stated. Otherwise, it's impossible to understand the result of your analysis. Then after defining the reason, you have to disclose who are the people you are talking to, and you have to define the reference unit that is collected to the result. This is called functional unit. It's a very important argument that we see later. Then you have to define and state the system boundary of the analysis and report in assumption, exclusion, or justification. As mentioned before, the functional unit is very important. According to its definition, is a quantified description of the performance requirement that the product system fulfills. Now, I introduce another term that is product system. Basically, this is the terminology to indicate what you are analyzing. So it can be a product, a process, or an entire service. And I want to stress that the functional unit should identify the performance requirement. And to do this, we can use, to help us, this table. So to properly identify a functional unit of your study, you can use these 6 questions to identify the properties of your functional unit. So for example, let's start from the first. You have to reply to what? The function or service provided. In the case of a shopping bag, the function is to carry or shopping from supermarket to home. Then how much? So the extension of the function. In this case, the shopping bags, you can state the volume that you want to transport. How well? In this case, without tearing, puncturing, and excessive deforming during the shipping trips. This is very important. How long? The duration, a minimum of 10 times. I want to underline that this doesn't mean that each shopping bag should last 10 times. It's that you are analyzing something with a time reference of 10 times. I can use one single bag, 100 bags, or 10 bags. Where, in this case, we are referring to the European market, and for whom by the entirety of consumers. So this question allows you to properly identify the functional unit. Sometimes it's almost impossible to identify a functional unit because maybe you are in a research and development stage, so you don't really know the final functionality of your product, of what we are developing. And in this case, what you are analyzing is the technical or declare unit. An example is, for example, if I want to produce copper oxide nanoparticles, and I want to know the environmental impact associated to these nanoparticles, in this case, I don't know the functionalities because I didn't use for some purposes. So I want to stress that I will analyze environmental impact related to the specific mass. Then something that I suggest you to do when you have to approach an LCA is to draw something, to draw the scheme of your process. And by drawing the scheme, you can simply identify what is called the system boundaries. Okay, let's start focusing on the square boxes. Here you have different life cycle stages. For example, we can start from the extraction of raw materials, then we have the production of some component, the assembly of the product, the use phase of the product, and the end of life. And each of these boxes receive input flows that are material, energy, and can produce output that are emission, waste, wastewater, anything else. When you define your system boundaries, you have to state what you want to analyze, because I can decide to use an approach called cradle to gate, and in this case, my environmental impact are related only to this big box. So I won't take into account the burden related to the use phase or the end of life of my product. Instead, I can use a different approach from cradle to grave and focus on the entire life cycle. This is very important to report, because if you see the result of some product, but you do not know in which life cycle stages are considered, it can be whatever. The input that I presented you before and the output are, of course, called input flows and output flows. And these, the identification, quantification of this generates the second phase of a life cycle assessment that is called the inventory. This is very time-consuming phase when you have to think of your product and consider, okay, what I need to put into my product. It's like if you want to prepare a cake, what is the recipe of my cake? And so I need to collect all the inputs, all the output emission that during the production process, during the use phase, during whatever phase are generated. And all these flows have to be related to the amount defined by the functional unit. This data collection can be far too questionary, as shown before in the presentation before. And here, just something that probably missed from the beginning are an identification of the life cycle stages. So usually we start from the raw material extraction. Then we can take into consideration the transportation, because when the raw material is extracted, we have to transport it somewhere. And we have to take into account the distance, the means of transport, the transported weight. And something that I want to stress is that transportation, it does not only happen between the extraction of raw material and the next phases, but it can happen more than one time during all the life cycle, even during the end of life, because when you throw something in the rubbish, this is collected, bring to the sorting facility, and then recycled. So we have transportation even there. Then we can have the real production moment of your product with the consumption of energy, water, production of waste. This is an emission, something that you do something and emit gases, emit wastewater, produce waste. About energy, it's very important is the type of energy that you are using, because if you are using energy, electricity produced from fossil fuels, you emit a lot of CO2. Instead, if you use energy produced from renewable sources, the emission of CO2, carbon dioxide, is very low, but maybe you are affecting other environmental compartments. Then you can have the use phase. For example, if you think of a machinery, a car, it consumes a lot of fuel during its life. And we have a big part of the environmental impact of the car life cycle occurring during the use phase. And then, of course, we have to take into consideration also the end of life. How can you dispose of, recycle, or use again your product? So, till now we have seen the first part, we had to state clearly the goal and scope of your analysis. You have to collect all the data that are able to model your system, to describe your functional unit. And then now we arrive to the life cycle impact assessment. In this case, the previous collected data have to be converted into a bunch of environmental impacts that affect different environmental compartments, different impact categories. And to do so, you can use software and databases and what are called methods that make able you to make this conversion. Something about environmental impacts is that to evaluate environmental impacts, we need indicators. In this slide, I try to graphically describe some of the indicators used in a life cycle assessment with some pictures. Probably all you know the global warming potential, that it's an indicator that affects the climate change category. And then we can have acidification, we can have indicators that evaluate the toxicity for human or the ecotoxicity for the ecosystems. Each of these indicators has different unit of measurement, as you can see here. And again, this is a sort of framework that you follow when you perform an LCA. So you collect the input-output, then you have all the indicators on impact categories, and in this case, I put it under the box midpoint, because these have a real effect on the environment. And then you can have what are called endpoint. So these are an aggregation of the environmental impact and that evaluate the impact on human health, resources, and ecosystem quality. An example, you have collected your input flows for some production of some materials, and you can use characterization factors. So for example, you have tabulated into the database information about the kilogram of CO2 related to the specific flows that you have measured before. We have measured in a laboratory, on your kitchen. These are an effect on global warming potential, and the global warming potential can have effect on human health, resources, and ecosystem. This is a list of different characterization factors and different methods, very specific, let's say. And then you can collect your result. You can present the result in different ways. For example, here, to understand this figure, you can see here several acronyms. Each of these represent a different impact categories or environmental indicator. As example, for example, GWP is global warming potential. And here you can have the breakdown of the result for different phases, like in a process or different life cycle stages. You can also try to break down the environmental impact for different ingredients, input. For example, in the production of these coated membranes, what you can see is that electricity is the main cause of environmental impact. So if I want to improve my process, the production process of this membrane, and in the end my product, I can work on reducing the consumption of electricity or change the source of electricity from fossil fuels to renewable sources. And then, of course, LCA allows also to make a comparison, solution A, solution B. The last stage, the last phase of life cycle assessment in the interpretation of the result. Of course, you have collected your result, you think about them, you try to interpret, and what is very important is to carry out sensitivity and uncertainty analysis, so statistical analysis to test the validity of your result. This is a framework. If you want to perform an LCA, you have to follow more or less all these steps. So you have to define your goal and scope, try to implement, to collect data for the inventory, to normalize the data according to the functional unit or the technical unit that you identify. Then you can choose a software, select a proper database. Here a list of databases. This database contains information of flows, processes. So for example, ethanol. If you use ethanol in your production process, in almost all the databases you have information about ethanol is produced. So how much energy is involved in the production of 1 liter of ethanol, how much fossil fuels, resources, and minerals, and so on. Then after the selection of the database, you have to select impact method. This is a list of impact methods, and this converts what you have collected as flows into environmental impact. Sorry, and then you perform the impact assessment, and then you interpret the result. Since here there are a lot of researchers, what I want to point out before I end up my talk is that if you collect information at laboratory stage, you can obtain a result with very high environmental impact indicated by these orange, yellow bars. Then, if you have the possibility to carry out the same process but at a pilot scale or even at industrial scale, you can see a strong decrease of the environmental impact. And this is very important to take into account and to try to forecast if you start analyzing your product, your production process from the first design, from the first research and development moment. The message that I want to bring home is that, of course, LCA allows to increase the knowledge related to environmental impact of a product or process. It can be used as an eco-design tool for comparing 2 or more functional equivalent solutions and improve them step by step, day by day. And in the end, the result can be used for communication, both for market application, but also for decision makers. Before closing, I would just to suggest you, if you are more interested in the safe and sustainable by design, topic, you can use this QR code to access this website. That is the Integrano website that can provide you webinar, workshop, and piece about knowledge of safe and sustainable by design. I hope that you enjoyed the presentation, and if you have any question, I'm available now, later. Thank you.
Okay, thank you very much. For the sake of flow, we will save questions for when all the speakers are done. And the next up should be Jonas Hoffman, I think, giving us a from GreenDelta, giving us a presentation on LCA for chemicals.
Yeah, good morning, everyone. After we have seen already now the introduction to LCA, we dive a bit more into a particular part of LCA, the inventory, which is a lot on time consuming. Would you say? Okay. Perfect. Yeah, I will not repeat most basic steps of LCA and also the idea of LCA, but I think it's a great on to SSbD and to sustainability in general. But what we focus on now will be the inventory analysis. So we will look into chemicals and how basically the inventory is built. For this, as was already said, processes are very often based on information like how much energy is used, how much raw material used, how much precursors are used. We need also to know what we produce. Very often in chemical industry we have byproducts, which also need to be taken care of in that logic if there can be trade-off. Direct emissions would be nice to know in that logic, to air, to the ground, but also there are things occurring which you need to be all aware of, but it was already said. Now it comes a bit more practical. So if we work with chemicals, so the slides will be distributed anyway, we need to differentiate a bit what we have kind of the governments of and what not. So if we work in a industry and we produce a new material, it's kind of it's called foreground. So we have the capability and we know what we're doing and we have kind of the hand on the process. So we know the details, how much energy is used, how much materials are used, which is also here by the GRC nicely displayed as an innovative technology. And we have a background which we rely on data from someone else, secondary data very often. In LCA, we can see here, so if we produce a new material, we have reagent A, reagent B, working together to make a new material which can be used. And later on also we need to consider the use phase and the end of life, which is also not in our direct capabilities, but very often somewhere else happening, especially incineration or other things happening, treatment of the waste. Going a bit more practical, I hope there are some organic chemists around after seeing so much nanoscience. So the case I want to discuss with you is very easy. It's a dye, it's methyl red, like an isobenzene dye, it's an indicator. And this molecule, e.g. I want to synthesize in the lab, I shop those two chemicals here. So I purchase them, but I have quite details about how to process it, though I don't have any information about how those are produced. So I need to find the data. And this is what it's all about today, and I will discuss today with you. Very often, as already said, rely on data from background databases. So if I want to look for environmental information or production information, I consider very often commercial and non-commercial databases, LCA databases like Econvent, Carbon Mines, DF 3.1 database from JRC, but also Gabi can be used, and I find the data then very often there. So now we go more. It's a training school, so we go more to a applied case. For this guy, enteric acid, you can go to several websites and look for the information for this molecule. So I took this GLAD website, you put down the name, and then you find kind of a lot of hits, like 20 hits of it. And actually there is data, which is very lucky in, I think, LCA world, because now we have data on it. And then we can also see where is the data from. For instance, here, all 20 entries are from Econvent. So you will have to use the Econvent database to use the data set for this molecule. There are also more information, which region is available, as you can see here, what is the modeling approach, etc. If it's for free or for sale. But at least this helps you already to use these databases. In chemistry, we have like SciFinder and Reaxys, but here there is not that equivalent for it, but we have at least this search engine. So we're lucky we found it. Something I want to teach you today, which is important, there is something called here process type unit. It's a bit like, okay, it's specific, what does it mean? It's very important. So unit processes kind of display in a deaggregated form or disaggregated form the production of a chemical. So you can follow the whole supply chain and really understand what is happening in which process. It adds up to transparency, but also you understand where things are coming from. The opposite kind of a unit process, our system process, everything is aggregated. Like he said, baking a cake, so basically you have everything together aggregated, the elementary flows there are, and you don't have a good overview of what's happening. And normally databases and also companies, they share the data in aggregated form, so you don't understand how they really produce it. But I just wanted to give you the idea why this is important. Also here, a good example from our software is how to produce a bicycle. On the right side, you see basically the ingredients to produce a bicycle according to the database, and the ways produced, etc. So it's very transparent. Left hand, you just see the elementary flows. So everything which is taken from the ecosphere and emitted to the ecosphere. So you can't really, from this, say how it's produced. At least you have the data then, but it's very aggregated. Coming to the more classical case, you put down a chemical, like this dimethyl aniline, and you find zero data. So that's why we have LCA consultants, because we need to find the data then afterwards. It's very common that there is no data at hand. So you see there is no entry. And this is kind of the idea, what we do if there is no data. And there has been some literature on this already. So JRC described it quite nicely, what to do in that case, but originated on this chart published in 2019. And the idea is a bit what to do if you don't have data. You go from the worst option to the best option, also like time consumption from the lowest to the highest, and accuracy from the lowest to the highest. And I will walk you through, depending on the time of it, through all the options. The worst one is always you omit the data. We can't do it for reagents because this would be problematic, but we could do it for some parts of chemical reactions for sure. You could use proxies, so you say, I use PBT, but I have a PET data set, so I stick to the PET. You need to justify it, but it could be done. And then we go more and more to other levels, which I will show in detail. So easiest step, fastest step. Omit, like proxying is a very fast step. So we say, for instance, we don't have dimethyl aniline, but we have aniline. That's fine to us. I think it's fine for like screening. You can, or you can also add methanol then to make it equivalent for the methyl group, but it's the fastest method. What some people do, also LCA consultants, professional ones, sometimes they stick to proxies which are called organic chemical. If you have no clue, it's fine, but I don't like this approach too much because it's a very broad approach to do it. Other way around would be omitting. So for instance here, in the reaction to produce it, there is HCl introduced at that moment. And if you don't find a data set for HCl, you could also substitute for it by not putting anything. This can be done very often if you use catalysts, you can omit them. If they're highly specialized catalysts, of course, then we lose the criticality maybe, like the material criticality in this dimension, or if it's used to a lesser amount. But it's not the best option. Then we also have module 5, which is kind of using something very similar to QSAR models, but here not predicting toxicity, but the environmental impact. So it's kind of it's a linear approach and a regression model to predict impacts based on molecular structures. There's something called the FineChem tool. FineChem 2 model is coming up soon, and they help you to directly get the impacts. You don't have a lot of information about production ways, but at least you can predict the impact. It's not the worst option, but also not the best. There is another method called stoichiometry. So what we do at the end of the day, we say we don't have data for this molecule, but we have data for this molecule, And according to literature, you use methanol to synthesize it. So of course you need to find your way, but then you use methanol, aniline, both of them have data sets, and predict the production of this guy. So again, it's highly underestimating environmental impacts, but at least you have data, and it's better than omitting anything. There are some details. I will not go into detail today, but I mean, I'm here, you can talk to me, and we can discuss this also in detail, what to do. Yeah, and also I wanted to say it's a bit, organic chemist, it's a bit like Lego. You can retro-synthetically analyze how things are produced. This also helps you a bit. And the highest grade method, of course, I hope that we have some chemical engineers here, is to really go into detail and make mass energy equations really balance out, do like simulation of stirring, of distillation, really go into detail of the reactor design and look into the details. There are a lot of paper of this. They're also cited by JRC, and also in most cases then you use the software to simulate the real process. So this is the highest grade method there is, but there is one higher, which is, we have to skip this unfortunately, the method 0, which is having actually data. So production data, of course, is the highest grade. If chemical companies publish their data, like Plastic Europe, like an association, is publishing like the production, for instance here, European-wide for ABS, you have a big and good overview of the production, or you look at databases and they potentially have good data on it. So this is always the highest grade, but of course I wouldn't tell it if it's already there, but if you're lucky, you can have the data sets according to this method. Yeah, coming to the conclusion already, I explained a bit what is the foreground, what is the background, where to find data, also what is the unit process, system process, how to follow this logic. If there are questions, feel free to ask me, and also how to fill data gaps, which we are often occurring. Some final remark from my side. Today I just presented how to model the production, like cradle to gate, but life cycle thinking is also the whole life cycle, and as you can see, it's a big other part which we are missing. And I want also to tell that the focus here should be equally also put on use phase, end of life, and everything which is related to this. And with this, I would like to thank you. And I think questions later.
Thank you very much, Jonas. And the next speaker up is Anna-Lia from the Technical University of Denmark. She will go a little bit more in detail on the environmental pathways assessment. Thank you.
Thank you for this introduction, David. So now we've heard a little bit about the background on LCAs, and as David just introduced me, I'm Anna-Lia from the Technical University of Denmark, and I'm both here as a participant, but I've also been invited to speak about health, environmental, and life cycle impact assessment. As this is normally something which we teach during a full 3 weeks course, I'll give you the Maggie dice, you know, the German Maggie dice of this, and focus on impact pathways. But before we get thus far, I just want to have a short show of hands of how many of you have actually worked with life cycle assessment before? Can you just put your hand up in the air? Okay, so a few. How many of you can keep your hand, it's a bit of an exercise, this whole session. How many of you have then worked with impact pathways too? And you can lower it down if you have, and you can keep it. So only a few. Well, let's jump into it then. To get you just, there we go. To give you an understanding of what we are aiming for in this 20 minutes is that I hope that you will be able to explain why it's necessary to do impact modeling, also to be able to outline concept of impact pathways using examples for example, chemicals and consumer products. And then also finally evaluating the chemical alternatives with regards to trade-offs and life cycle impacts. Okay. But first of all, let's just begin with a shared vision. Because we have a world that we want to live in, and this world, we would preferably want to have some clean air, clean water, also that our ecosystems are protected and that we generally have a sustainable development. But to get there, we need some type of intentional planning. To do that intentional planning, we need to understand the impact pathways that really gets us there. Because we would rather not want to have pollution or both of our environmental systems, waterways, of our air. We don't want this environmental degradation that puts our future at risk. So, and this is just not, it's not just like random things I'm mentioning, it's actually scenarios that we are seeing out in the world right now. It's real conditions that millions of people face. So unless we understand these pathways that brings us there, then it's going to be really difficult to stop them. We talked a bit about life cycle assessment, and normally we have this black box which is called the impact modeling. So we have the inventory, we have the black box, and then we get to some type of damage. I want to jump into understanding this black box together with you. So in the inventory, we first have the emissions, then in the inventory we have some kilo emitted per functional unit. Then in the impacts, we combine that with a CF, so a characterization factor, which is provided an impact per a kilo emitted. And then finally we get to damage, where it's like total damage per impact per functional unit. And as one of my colleagues mentioned earlier, the functional unit, it could, for example, be this use of 0.79 grams of deodorant per day applied on the skin of an adult user. So we have something we can compare everything to. For a product, for example, it could be kilos of chemical in a product per functional unit times the characterization factor, which would be the impact per kilo in the product, and then equals then the total damage, so the impact per functional unit. But to get there, I just need this to fall. I want to do just a steeper jump into what a characterization factor is. Because to build this characterization factor, we need to have some type of emission. So emission, I'm an emission now of soap bottles, soap bubbles. This emission, as you see, it has a fate. So it's moving somewhere. I can model where it's moving through Python or various wind models, however. When it ends up having this fate, and we just, maybe that works better. I need some more of them. There we go. When it has this fate, it would also lead to an exposure. So maybe, not fast enough, but if I touch it, it might have some type of skin contact with me, and therefore it can lead to some effect. Maybe it has an irritation on my skin. This is all steps that we can then measure and brings us finally to the damage factor, where we sum it down into, okay, it's the human health that's impacted because I have some type of skin irritation. So we go from the emission, the fate, the exposure, the effects, and then to the damage. I want you to just take a minute. We're a bit timed, so I have 3 clocks over there, and they are timed for 1 minute. And I would love if you take 1 minute to just thinking individually of what the potential direct and indirect impact pathways show of how a chemical in a cosmetic product can harm humans and ecosystems. And then taking 1 minute with the partners, just turn around and keep an eye on the clock too. And then we'll take 1 minute sharing it. And I'll also give you an auditive cue when the first minute is gone. Yes? Clear? Hopefully. Just to have you remember, this is kind of the ways that we can go. And our first minute starts now. Okay, so we transition over to discussing for 1 minute with a partner on what an impact pathways could, for example, be. And I hope to hear your loud voices discussing with your partners and sharing the ideas that you've just thought about for a minute. It can be chemicals, colorants, fragrance, yes. It can also be other things, that's cosmetics, if this is too far away for you. But we'll jump over now into 1 minute of sharing. Does any of you want to share what you've been discussing? Yes? No? Yeah? Yeah, that's a good, so that was waste streams moving into to soil and water. So yeah, we have like kind of the start and somewhere there in between. So we really go from these emissions, then we have these, the fate, the exposure, the effect, and then the damage, right? That's the steps that we have. Does anybody else want to share? We still have 15 seconds. Yeah, David? Microbeads in scrubbing products. Yes, and what would you imagine the steps would be? Mm-hmm. Yeah, so we use the microbeads on for washing us. We both get them on the skin. Then we also emit them with our wash water. So we have different interactions with the components, both ourselves. So we have maybe some damage to, maybe we get an allergy reaction or something, or hormone disruption. And then we also can have, what you're moving into is also the wash water, so also for the ecosystems. That's a bit of a further path to go down, because we have the wastewater has to be going to a recipient and everything. But great, thanks for joining in. There we go. Okay, so if we bring it all together a little bit, we had this emission, and what we touched upon before is that we have these midpoint categories. These could, for example, be climate change, eutrophication, acidification, land use, ecotoxicity. It goes on like that. You can have a lot of different depending on which impact assessment method you use. We can then bring that further, as actually was mentioned before, to the endpoint, so the human health, ecosystem health, and resource depletion. When we do that, however, we should also be aware that we actually introduce a bias, because we have some type of weighting. We have all these many categories, and we say, okay, how important is climate change compared to human toxicity, climate change for human health, when we go to the human health, right? So often we want to actually prefer to stay at the midpoint level here, and that's the endpoint level. If we give a bit more of an example, I've picked out here human toxicity impacts, where we have this emission, where we have kilo emitted per day. That emission is then linked to the fate factor, as I said before, and then linking up to the fate. The fate factor can be provided in kilo in the compartment per kilo emitted per day, and so it equals out. If you're mathematically a little bit keen, you see it ends up with kilo in the compartment. We touched upon earlier, both yesterday and a little bit today, these environmental compartments, they interact in different ways, and that's just briefly shown here. So you have the air and the water and the soil interacting in different ways. Going from the fate, we then move over to the exposure, where we have the exposure factor linking with a kilo of intake, so maybe it's either touching me or I'm eating something, per day, per kilo in the compartment, because we bring that from the fate, and then over to the exposure, where we then have kilo intake per day we end up with, right? So I'm eating something and I'm intaking these things. That finally links to the effects, where we end up having with disease cases per day, and that links by the effect factor, which is the disease cases per day, per kilo, per intake, per day. So again, mathematically, this is one type of impact pathway. You can also have it for ecosystems and other aspects. Keeping this in mind, I want to have you exercise a little bit again. I hope you have your phone with you. If you can find your phone and then scan the QR link, it's a QR code. The QR code, because the exercise here is that we want to look into a safer and more sustainable alternative, SSbD. So I hope you're a little bit familiar with this. We have two different chemicals, the formaldehyde and the phenoxyethanol, and we have a consumer risk and life cycle impacts. The consumer risks have the units in front of them, which are none, and then you have the life cycle impacts, which are given in dalis per day. The acceptable risk should be noticed for the consumer risk is that cancer should be less than 1 to the power of -6, and non-cancer hazard quotient should be less than 1. So the question is, can you select the safer and more sustainable chemical? And the timer has started. And you will only get half the time, because I already saw that most of you used the phone and linked it. But I didn't, oh yeah, I do. And you have these different options. I keep the time here. You can see. I can go back, yes. In the QR code, you should also have the question. So, okay, you don't have the table, of course. Okay, I see half of you have answered. If the rest of you slowly can answer, and then we'll jump to the results. Thanks for participating in that. So these were the answer options, and you saw them up there. What we are going with as the right answer is no, but phenoxyethanol has low risk, because it's commonly way higher than the life cycle impacts. And that means that the phenoxyethanol, for now, is the winner. So I need to go around here. There we go. Oh yeah, and what you might also want to actually know is that we had just around 22% on answer 1, and we had almost 50 on answer 2, 3% on answer 3, and 30-ish recipient or answers on number 4. I couldn't make it interactive, but I can upload the results later. Why so? Well, the thing is that as I said also here, the acceptable risk is a non-negotiable risk. If it exceeds the acceptable risk for consumer risk, it will be discarded as a possible alternative or solution in a product. So even though I would love that the life cycle impacts were also just at least higher weighted, for now we have the phenoxyethanol as the one, even though it has slightly higher environmental impacts. And that brings it to the end of my session. Thank you for your attention. Thank you.
Thank you, Anna-Lia. And then the next speaker up is Arianna Livieri from GreenDecision, followed by her colleague Martina Menegaldo a bit later.
So, good morning, everyone. I'm Arianna Livieri, and today me and my colleague, Martina Menegaldo, are going to talk to you about the Prospective LCA. So, we will start with a question, then we will see the definition and the aims of the Prospective LCA, the Prospective LCA in the safe and sustainable by design context, the challenges, the methodologies, and the scenarios construction. So, the question is, how can we ensure that an emerging technology is safe and sustainable from the outset while delivering lower environmental impacts than the existing technologies they aim to replace? So one of the answers can be the Prospective LCA. Compared to a classic LCA, it's a more advanced approach. And if, for example, in a classic LCA use current or past data to model, the focus of Prospective LCA is on the future scenarios. So a Prospective LCA is when an emerging technology that is produced at a small scale, its model if it is an advanced stage, so a more developed stage. So if these emerging technologies is used by everybody in their everyday life. So the Prospective LCA has different aims, but we can see 3 principal aims that are to inform the developers of the beneficial change that you can do to technologies. In this way, you can avoid wasting time and money. The second thing is to support the decision of the policymakers looking to fund projects. And the third one is to push the manufacturers towards the best version of a technology, so the most sustainable version and most sustainable application of a technology. So, as we see, the basic aim of the Prospective LCA is to have something sustainable from the beginning of the life of the innovation process of the emerging technology. So we need to have something that is safe and sustainable from the design, and that's why we can go in parallel with the Prospective LCA and the Safe and Sustainable by Design. I know that yesterday there was a presentation about the Safe and Sustainable by Design framework, which is made of 5 steps to assess safety and sustainability. And we know that the step 4 is about the environmental sustainability assessment. And in this step, you can apply the LCA. So we can also apply the Prospective LCA. And this framework can be applied from the beginning of the innovation process of an emerging technology. So while doing a Prospective LCA during the innovation process, there are some things that need to be considered, some aspects, some constraints, and these are 2, the knowledge and the timeline. The knowledge is the amount of information related to that specific things that you are going to assess, because you know that at the beginning of the innovation process, the amount of information is low, while going up with the innovation, this amount of information is higher. The second thing is the timeline that goes from the beginning of the innovation process and the placing of the end product on the market. So while doing LCA, we know there are some challenges, and while doing a Prospective LCA, there are more challenges, and these are divided in 3 blocks. So we have the block related to the uncertainty, that related to the comparability, and the last one related to data. So we know that while doing a classic LCA, there is always uncertainty, because yes, we use real data, but we also use information that comes from the bibliographic research or from the database. But here you have more challenges, since you use that information that are not always real, but you try to understand what can be the impact of something in the future with a perspective. So you have uncertainty related to the parameters, to the scenarios, to the model. Also, you have challenges related to comparability, because in a Prospective LCA, you try to compare an emerging technologies, where you know, we can say almost nothing, with a technologies that exist in the market and you know almost everything. So you have a problem to compare those type of things. So there are challenges trying to identify the aim of the study, the functionality, the system boundaries, the life cycle impact assessment methodologies. And the last challenges is related to the data, the availability, the quality, and the scaling of data. And all these 3 are the challenges related to the Prospective LCA. And now my colleague is going to talk about the methodological approaches.
Thanks, and good morning, everyone. So yes, with me, we will see a little bit in deeper how to set up a robust comparison between an emerging and mature technologies. So first of all, when we are setting a comparative analysis, we want to align the different technological readiness levels of the 2 or more technologies under assessment. As we saw before, one of the first decisions that we need to take when we are performing a life cycle assessment is the definition of the functional unit. And this could be quite challenging in prospective life cycle assessment, since for emerging systems, functionality may not be fully defined. So this could affect the results, and could be also depending by the quality and technical specification of the product or process under assessment. Another important thing to set up is the system boundaries. So first of all, what you are assessing. You can assess an intermediate chemical, and in this case, it's totally fine to set up a from cradle to gate study. While if you are assessing a final product, you should include also the use phase and the end of life, and those could really affect the final results. But once again, it could be very challenging, so you should use the scenarios. So while you are try to describe the future, you should use the scenarios to try to understand how this future could be. Before with Arianna, we saw already this kind of graph. The main scale analysis that we are evaluating are two, basically, the time scale and the technology scale. We are, in Prospective LCA, comparing an emerging technologies versus conventional technologies. Probably we have some good data for the conventional technologies, while for the emerging one, we have typically lab scale data or pilot scale. And we want to scale up this kind of data to try to understand how these technologies could work once that we reach a higher TRL. But this is not enough, because if we do this, we are modelize what is the status quo. But we want to scale up also in terms of time. And this should be done not only for the emerging technologies, but also for the conventional one, because we want to understand how in our way, our world will work in the future. While you are upscaling, you are introducing a lot of uncertainty. So also in this case, the scenarios could be very useful to try to picture this kind of uncertainty. Another scale is the geographic scale. We can have basically three main scale. The small micro scale, when we are early quantification of life cycle impacts for emerging technologies. The medium scale, that support for scale up and integration of new product or technologies in the current and future systems. And finally, a large macro scale for regional or national policy evaluation. So according to this, we can also identify three main scenario types. For the near future, we have the predictive scenario that explore what might happen. And then we have other two scenarios that are the explorative, that investigate what could happen under different assumptions, and the normative one, that take into account how could happen according to specific goals. So we have the main decision that you should take when you are performing a prospective life cycle assessment. This is a very simple example of a typical case studies. We are assessing an innovative bio-based chemicals and comparing this to a traditional one. So we have two main alternatives. But when we are upscaling, we find different alternatives for the future, for the innovative alternative. And build on this, we can create different main scenarios. But then, if we go in deeper, we can identify other several parameters that could influence the scenarios, such as type of ingredients that we want to use, type of energy mix, type of transportations, and so on. And by identifying those parameters, we can create different sub-scenarios. And in the end, I would just present you a typical type of normative scenarios, because it's quite common to try to include also scenarios based on the shared socioeconomic pathways and the representativity concentration pathways by the APCC. This could be done within the Prospective LCA with several tools. One of these is Promise, that integrates project climate change scenarios from integrated assessment models. One of these is called Image, and as you can see in the graph, we have 4 different IPCC scenario. One is a sustainability scenario, while the other 3 are the middle of the road scenarios. And in these examples, we see parameters covered through the use of future background scenarios for different electricity supply mix. So this could be very useful to integrate in our prospective life cycle assessment. And we can see how the results could turns if we change the future that we are reaching. And of course, you can do this for a long time horizon according to the normative scenario by the APCC. This was just an example, but with Prospective LCA, we can really assess different types of scenarios. This is just one normative, but yeah. And thanks for your attention.
Thank you very much, Martina. Now, the last speaker for this session, for this great session, I have to say, is Tomas Rydberg. He will join us online, and his presentation will shift a bit the focus from relative sustainability to absolute one.
I hope you can hear me and see me.
We can hear you and see you. Also, feel free to share the presentation whenever you're ready.
Okay, I will do so. Just as long as I find the right sharing option. Not completely used with Zoom, actually, so forgive me for that a little bit. Here we go, somehow. And you should now see a screen saying absolute sustainability in life cycle assessment.
We are seeing the screen. It's still in your PowerPoint mode. Now it's in presentation mode. Thank you very much.
Okay. Hi, everybody. I am sorry I cannot be with you today, but for some private matters, I had to stay here in Gothenburg, which I am sure is a bit colder than Venice currently, but we are expecting the Spanish heat wave coming in over the weekend, so I will have my share of the heat anyway, I suppose. I understand you have a very good time down there, so I will try to contribute my best to the session today and talk a little bit about absolute sustainability in life cycle assessment. I've been very energized by hearing Annelia and Martina and Arianna before me. So let's see what I can bring here on the absolute sustainability issue. So, for sure, what is absolute sustainability in LCA and why is it an issue? Well, there are many reasons, obviously, and the discussion has been going on for a while, but I think in the current situation we are, it's predominantly a matter of, let's say, when we start talking about SSbD and we want to somehow put sustainability alongside safety, it's considered that safety is being evaluated against absolute criteria, which it is, and you heard from Annelia an example of that. So, and the properties there are measured on the chemical itself, typically. So if we want to have like symmetrical, if you could say it like that, comparison or rather assessment also on sustainability on the same level as we do for safety, there is sort of a desire to have also an absolute aspect when it comes to sustainability. So we have a bunch of challenges that are obvious when it comes to absolute sustainability, and some of you in the audience are probably well acquainted with LCA, so it would not be a surprise to you. And this is not an exhaustive list by any means, it's just a few examples that I want to address here, and of course there is a relatively short time that I have available as well. So first point is actually how to understand the meaning of absolute sustainability. What does it actually mean? And of course, even if absolute indicates that there is something very strict and precise about it, I think I need to put in a bit of a disclaimer here that even if we talk absolute, there is absolutely no agreement exactly how to define it. So it's always nice to discuss this thing about not being so precise that you assume that you would be. And of course, if we compare the safety aspect to the sustainability aspect, we have so many more impact types that we want to address in LCA. So already there, we also have a problem. Even if we can define some kind of criteria for absolute sustainability, they will typically be, let's say, defined on an impact category level. So midpoint, if we go back to Annelia's presentation, normally at least, or that's how it's done currently in the current approaches. And of course, how can we then deal with that? Should we always go with the most, let's say, strictest requirement, or what's the way of balancing these out? And finally, or among the three that I listed here, of course, there is the issue that we probably understand sustainability on some kind of relatively high level, and ultimately it's a matter of large scale systems we are talking about, and then how do we define that down to a product level? That's really tricky. So how can we tell in one specific product if it's absolutely sustainable or not, the way we understand sustainability currently? And I will try to address these three different challenges in different ways here. So first we can look into the framework of socio-ecological indicators that was established or published in 1996. I'm typically going to refer mainly to Swedish research here because that's the one I know better. Of course, there have been other researches as well, but let's start here anyway. And these four principles of socio-ecological sustainability or indicators of sustainability have been used quite much on the global scale in, let's say, movement or an organization called the Natural Step and the Natural Step Foundation. And they are outlining what the authors of this paper and the team around them chiseled out as four key elements if we want to achieve a sustainable society. And as you can see, they are all formulated on a very high level, in fact. Concentration of substances extracted from the Earth's crust cannot systematically increase. And of course, increase then in the living environment is what we refer to here. So that goes, let's say, with naturally occurring substances. It could be heavy metals, for example, as a good example there. Secondly, the concentrations of substances produced by society cannot systematically increase. We can relate to PFAS there as an example, or any kind of persistent chemicals, basically. Third, degradation by physical means, typically by ecosystems, cannot systematically increase. So we can't eradicate land, and we cannot change land, so it's not useful for producing food, basically, if we want to boil it down to something very directly meaningful. And fourth, we need to make sure that we distribute resources justly among, in the world, basically, for human needs. So these were the four criteria, and then in fact there was also a group of researchers that wanted to try to transform these criteria into something that made sense in a life cycle assessment context, specifically for product development. And of course that's a little bit where we are when we talk about SSbD as well. But you realize maybe that these four overarching elements have to be interpreted in a certain way to be meaningful in a life cycle assessment context. And this is exactly a similar situation that we have now. Fast forward to the planetary boundaries agenda that happens to be, let's say, emerging from the Stockholm Resilience Center. So it's also kind of a group of Swedish researchers that have been instrumental in developing this. But then, of course, there has been a lot of internationally renowned researchers involved as well. And this picture or graph or graphic is directly taken from the Stockholm University website for the planetary boundaries concept. So they outline the 3 so far development stages that have been there, and it's very handy in that way that it outlines all the main development phases. So you see that it started in 2009, and if I'm going to be a little bit critical, if I go back to the original source document by Rockström, it doesn't look exactly like this. Particularly, they point to the fact that the novel entities are probably, they in fact use another word terminology there, and they say that it's probably exceeding the limit, but they haven't been able to quantify it. But you can see that there are a couple of things that are interesting here for the continued discussion as well. First of all, you notice that they divided the planetary boundaries into 9 segments. So all the graphs have 9 pie chart pieces, let's say. In fact, in the latter 2, there has been there has also been a further subdivision of a couple of them, as you can see. So in fact, there are not 9 specifically, but anyway, let's say that there are 9 main categories. And then they have gradually developed, let's say, the boundary concept and the inventory, to what extent they are exceeded for more and more of these over time. And you have the whole list of references at the end of my presentation, and also you can see the link to the actual graphic here at the bottom of the page. So, okay, that's all fine, but what can we do about that? Well, now I think it makes sense now to take a look at how can we interpret the planetary boundaries in relation to life cycle assessment, because here I just indicate that, okay, we have the 9 main categories from the planetary boundaries framework, and then as I indicated, there are a bit of subdivision for the biogeochemical flows, which is divided into N and P flows, so nitrogen and phosphorus related ones. There is also the freshwater category, which is divided into 2 categories, and also another one that's divided. And then we compare with the established impact categories list in the Joint Research Center guidance, or in fact now the Commission recommendation for environmental footprint. They don't match, at least not in detail. You can see at the top of the list you have climate change, stratospheric ozone depletion. They are essentially a 1-to-1 relation, but then to bring it down to something, or to apply the planetary boundaries framework, we need to interpret these categories, or maybe vice versa. We need to develop additional planetary boundaries if we want to apply that directly to the impact categories in the environmental footprint list of impact categories. So that's a challenge, of course, and that has been tried out. So colleagues of Analia in DTU were first out. I don't have exactly the reference to them here. It's Anders Björn and Mikael Hauschild and others who did that work, but I would rather go in the direction of looking into this graphic, which is a compilation I did several years ago, and it relates to the stratospheric ozone depletion, and there are a lot of numbers, so I will try to walk you through it. If you see my pointer, maybe someone can shout out if you see that I'm moving my pointer here or not.
Not really a pointer, but
okay. Or something. Anyway, I will tell you what is there in the different columns. So the overall idea of this picture is to indicate that depending on how you define the criteria for a critical boundary of some kind, you will end up with different numbers for the actual critical boundary. And just let's start in the middle. When the main international agreements were reached about the protection of the ozone layer, this was in the late 1980s. So the emissions that were, let's say, globally on ozone-depleting substances could be calculated in the order of 1 million ton as ODP units. And this was seen as unsustainable, obviously. It was modeled that the concentration that we would ultimately achieve in the atmosphere would be around 15 ppb per volume if this emission rate would continue. I haven't even seen any attempts to calculate the actual damage that would cause, but that was there. Now, if we rather consider the concentration that was actually there in the stratosphere in 1988 specifically, it was around 3 ppb, which calculating backwards would lead to something like 0.4 million tons in ODP equivalents. And the estimate was that if we maintain this concentration, and these were like indications that were already seen given this concentration, was that there was a increased mortality based on skin cancer with something like 1 to 2 deaths per million persons per year. Interestingly, there has, in some aspects of health economy and health preservation, or let's say health science, been suggested that we might have 1 death per million people per year as a kind of an indicator or kind of a tolerable level. It could be that you can't really indicate, well, you can't really measure if there is a smaller impact happening. But anyway, if we have this death, or a certain damage level of 1 death per million person per year, it would be then, of course, a bit less than these concentration and emissions as calculated for 1988 situation. So we would end up with something like 2 ppbs in the atmosphere, and corresponding to roughly 0.3 million ton ODP equivalents as the allowable emissions, basically. Now, for the ozone depletion mechanism, there was this specific let's say, tipping point available that if the concentration increased beyond, or that was seen like looking backwards in the measurements that had been done, that at the point where the concentration exceeded 1.5 degrees, when the concentration increased beyond 1.5 ppb, the phenomenon of the ozone hole over the Antarctic region would start to appear. So this was then used as a very important, let's say, boundary to get below. So that would essentially mean that the emissions need to go down under about 0.2 million tons ODP equivalent. So my point is here that depending on your criteria for the damage level that you are kind of willing to accept, or if you strictly want to go to a pre-industrial concentration, you will end up with different levels of allowable emissions, if we put it this way. So it means that the sorry
to break your flows, but unfortunately, remotely you cannot see the sign for the 2 minutes limit, and we are kind of already late. The morning started late, so I would invite you to maybe try.
Will you cut me short, or can I just use my 2 minutes?
I'm not cutting you short.
Okay, fair enough. I will just
of the
jump over the next slide, basically, but we can say that the global, let's skip that one. So my point here is that the threshold criteria, depending on how you define them, will look differently, and I showed you specifically before the ozone depletion criteria. Now, already in the mid-1990s, in the Netherlands was developed the Eco Indicator 95 method, and they specifically used this probability of 1 death per year per million people as the threshold for ozone depletion, whereas a system I was involved in developing myself used this concentration that would take us below the ozone hole as a criteria in another parallel model that we defined, and this has been presented in a poster at the CETA conference recently. Now, the European Commission, GRC, they made this kind of translation of the planetary boundaries into the environmental footprint context, and ended up with finding out that for some of the categories we have far exceeding the planetary boundary, and the number 1 here would represent the emission being equal to the planetary boundary on a global scale. So for 5 of the categories for which they developed these PB numbers and global emission numbers, they were exceeded, whereas for some they are not yet there. And this is, generally speaking, quite in line with the planetary boundaries research group own findings. Not exactly, but roughly speaking. And then there were, again, a number of categories that do not translate, let's say, from the impact categories of LCA to the planetary boundary concept. And I will skip this one, of course. Just mention that if you want to calculate some total score or relate to the planetary boundaries, you obviously need to use the same categorization models and versions of the categorization model. Final slide, actually. To summarize what I say, the planetary boundaries say very little about the sustainability of a specific product, essentially. So how do we translate the planetary boundaries down to the product level? And that's a big challenge, obviously, to distribute the allowed safe operating space down to the product level. What we have tried to do so far in the community is to allow, let's say, calculate allowances per capita, which obviously works, but it doesn't capture the products that the person will, let's say, make use of. So it's not fully doing its job. Another approach is to go with the economic value of the product, which takes us a bit closer. It would essentially mean that you say that the impact of category X can maximum be the number of Y per euro of a product Z. So it would definitely link the sustainability allowance to a product for sure, but there are some other challenges related to that, obviously. But final statement, whatever approach you take, you will not get around the fact that you need to do some kind of agreement among stakeholders, what criteria to use, how to interpret the planetary boundaries, or whatever context you use for the sustainability definition. And ultimately, the criteria and the, let's say, definition of sustainability will be something that is defined by ourselves. So thank you for listening, and these are the references to the different inputs I used, and maybe there are some questions.
Thank you very much, Thomas. Thank you, really. In general, thank you very much to all the speakers for your patience, your inspiring messages, and also to including Amaya. You collectively managed, we are only 5 minutes late to the original schedule, so thank you. And there is a little time for a Q&A session for all of you about LCA and sustainability in SSbD before we all head off to the coffee break. Are there questions from the audience? Yes, please, Jon?
Hi, good morning, and thanks for the presentations. This is going to be quite a binary question. It's about yes or not, right? And I don't want to be very tough. Something you were mentioning that I find quite interesting is that usually when we are designing a new material, product, whatever, we don't know what's the functional unit. If I'm an engineer and they tell me that I have to design mechanically a lift, I will ask, well, how many people do you want to carry and for how long? If they don't give me that data, I cannot design a lift. You were already mentioning that even not having functional units, we are designing materials. Do you think that's feasible? And the question goes for any one of you.
Okay, a brave one that feels like opening.
Does it work? Okay. Yes, let's say that we are not design, but we can analyze something. I mean, in LCA, in this kind of methodology, you can always analyze something. The fact is that even if you are not defining a functional unit, you can declare a technical unit, collect data for that one, make an analysis, and then in a second moment, improve the analysis by moving that one technical unit to a function unit if you want to incorporate the final functionalities. But you can, because it's not such a big deal. I mean, it's only a matter of calculating something and collecting information.
Anna?
Yep. Like this? Nope. Now? Yes. Wonderful. Okay, just to add on what Mattia just mentioned, you can use LCA in various ways. One is, yes, to what's called design a product. Another one is to optimize it. A third one is to say, okay, which one of these should I rather use? So it's really a question of, I have a lot of things out in the world already. Can I optimize them? Can I redesign them? And that's where the life cycle assessment tool and thinking generally can come in and aid. It can also be used, we didn't really touch too much about this, but it can also be used in companies, this whole way of thinking, to shift towards a more sustainable, well, planet.
Thank you. I think Thomas from online would like to add also to this question.
Yeah, I support Mattia's and Annelia's statement, and I think also Martina had in her presentation already the answer. You can do scenarios for different functions, but I will also say that if you are talking to someone who is, let's say, inventing a new chemical, they will typically at least have an idea or, let's say, a hope that their chemical should be useful in a specific application. So I don't think the problem is necessarily that we don't have an idea what the chemical should be used for, but we can define for what application we want to do the analysis. And then, of course, the chemical can potentially be used in many different applications, but in that case, we need to, of course, then do it over again for the different applications where we want to use it. And I was talking to a colleague yesterday, and we were discussing what if there is a completely new function and a completely new application. And yeah, of course, they exist, but they are extremely rare. So in 99% of all cases, there is some kind of substitution or improvement of functionality or something in place. And even if you go back to the chemical one, the one that develops the chemical typically has an idea of what kind of technical properties are they looking for in the chemical, which indicates what kind of application they are aiming for ultimately. Thank you.
Thank you very much. Are there more questions? Yes, over there.
Microphone maybe start.
Sorry. What, sorry, I didn't see the the microphone already in place. Please.
No, but go first. Thanks, first of all, for the presentations. I have two questions. One's for Jonas. I saw from the methods that maybe from a practical point of view, we would like to apply like method one on really specific ones. But from a practical point of view, which methods do you actually see when performing this type of LCAs? And the second question is more something that Arianna mentioned in the Prospective LCA about comparability, because that can be something very challenging if we're talking about already established versus emerging. So yeah, in general, how, from a Prospective LCA perspective, can you tackle that?
Yeah, thanks a lot for the question. I hope it works, yeah. Short answer for this. So as I'm a chemist, I know how to play all the methods. My coworkers who are not, like they're LCA experts and consultants, but from different fields, renewable energies, they stick very often to method 1 or 0, to the 9 or 8, like the really bad methods where you just omit or use proxies because they don't know how to model it. It's quite common. Of course, this is the way. It's not very good, but they also need to do like sensitivity analysis, which we discussed not today, but it's also they need to prove that this makes kind of sense. So yeah, we also, I skipped the slides, but we have also a bias on being very accurate in LCA. The more accurate you modeled, the more things you find actually, and that's also something which can happen. And we found already that this is also a bias if we really dig deep, but don't have a high TRL, we run into an issue that we overestimate also environmental impacts. So yeah, but normally I see also very often people using proxies or omitting chemicals completely.
Yes, okay. As you said, it's quite challenging to try to compare an innovative technologies with an established one. I think the first thing is try to align the TRL and then maybe try to include also the time horizon. So first of all, try to analyze how the innovative technologies could reach the established one in the technology environment. And so here we are referring to the data assessment. As we saw today with Jonas, there are several approaches that could be useful, of course. Some of them are more accurate. Of course, they need a lot of efforts. And so it really depends also in what kind of field is your study.
Okay, and then the last question for this session, but please remember that these great speakers will be at the coffee shop, at the coffee break. And I also need a coffee, guys, I'm sorry. And they will also host the training session after the coffee break. Please go ahead.
Yes, thank you very much for your very insightful presentations. I just wanted to ask, it's a safe and sustainability, and we have also some safety categories in LCA. So how do you see the relationship between the toxicity that some people doing safety measured in LCA? For me, I would give a bit hint. Jonas mentioned that in LCA modeling, people tend to think in terms of foreground and background toxicity. Well, foreground and background. So we should also start thinking about foreground and background toxicity in a way, because one of the options that we were analyzing were the case study, there was no toxicity for the users. But you could also have the supply chain toxicity, and that option with no risk for the user might have high risk for the workers of that plant producing that chemical because of the precursors. So that option might seem safer for the user, but in the supply chain, the background toxicity, it's affecting way more people or creating more toxic units for humans, for example. So how do you see this relationship between the toxicology assessments and the safety dimensions that we can assess in LCA? Thank you.
So from my point of view, I think Thomas is maybe the right person because he has more experience on this, if he wants to comment, because I have an opinion, but maybe he wants to start.
I heard someone saying that they wanted to have coffee, so I was kind of smiling when I heard the question because it's their answer could be very long. But there is no obvious answer to it because, yeah, we have the issue that in safety you look at absolute, or you compare with a threshold, and in LCA we more have a comparative approach. So they kind of give you different signals, and I think the main benefit of the LCA approach is that you achieve information about the chemical, or let's say toxicity-related pressures from other parts of the life cycle than only those related to the specific chemical that you are dealing with. I will stop there, I think.
Yeah. So I think my point goes in a similar direction. I mean, also we make a lot of effort to put the toxicity now into LCA, like of the compounds, but I always have to explain to people if it's not emitted also, if it's intrinsic, not emitted, I mean, there is no toxicity, it doesn't make sense to make the effort. So LCA is also not really good for a human toxicity impact category. If you know the weighting from the JRC also, it's not the best impact method. So maybe we should look at different ways. But I think it's an ongoing discussion, and we can discuss further at the coffee break, I guess.
Okay, thank you very much. Thank you all again. If you want to stand up for a round of applause. And now everybody's free to finally get a coffee, but please be back here by 11:30 because we are starting with the workshop. Thank you, Thomas, again. Grazie a voi, davvero.
Good job, everyone.
Means your entire panel is going to come back?